These are larger, so hopefully it makes sense. Shoot, I didn't know that they both keep popping up. It wouldn't take as much energy to take something when the electron's further away. As I move across, again, just hold on to one thing, which is it's all about the size of the atom. Atoms get smaller over here, so that means my electron is getting closer to my nucleus, so it's going to be harder and harder to remove the electron from the atom. And this is really important. This is why reactions happen or why they don't. It's about how difficult it is for the electron to be removed. All right, so we're going to draw a little picture. You should have a little space left. And I tried to find the, it actually was a really boring video, the World Championships of Tug of War. It was not exciting. Actually, the funniest one was a dad making a video where he did this bathtub of mud and soap, and then he pulled all of his kids into it, and they were trying to tug of war against him, but it still wasn't that great. But it's a tug of war kind of thing here. So you got the protons, and you got the electrons, and they're both basically pulling. So if I were to remove an electron, you remove one, well, who's going to win? Well, now I have less negatives than positives, so the positives are going to win. So what do you think happens in my cloud? Think it gets bigger, or do you think it gets smaller? If the positives now have more pull than my negatives, well, positives will be more populated than the negatives, so the cloud's going to get sucked in because every electron's going to feel more pull. Okay? So you need to know this. When you remove an electron, it becomes smaller. An atom becomes smaller when it becomes a positive ion, when I remove an electron. And today's kind of heavy note day, I get it, but we got to kind of be able to apply all this because this is actually setting a foundation for kind of the rest of the year of different kinds of big name topics that are going to apply to different chapters. You never put a negative in a chemistry equation. So it's not a negative electron. What happens is the electron ends up over there. So it becomes a positive charge. So your responsibility will be to know that, oh, when I have a positive ion, it's smaller than the atom because it actually shrunk. Okay? So that is ionization energy. Oh, did you need that yet? All right. Chris is ready. All right, on the back of your sheet for a second. There's not a lot we're doing with it. It's just I wanted to show this image. This is called successive ionization energies. And there's a huge table. And you're like, oh my gosh. It's can you read it? It's not can you make it. It's not like that at all, okay? And what I need you to do underneath successive ionization energies, just please write this. It's removing one electron at a time. Because ionization itself means to remove an electron. Bless you. So there's this big chart, and if you look at it, see how mine's colored, but you can tell. There's like all these values, and if you notice, and we're going to just look at one example, like the next value underneath is much larger than the previous one. Like 738, 1451, then 7,000. 578, 1,800, 2,700, 11,000. What this is showing is the difficulty of removing an electron. This is how, and I know the numbers don't mean anything to you, but you can compare them. Like it takes 738, I think this is joules, to remove an electron, then it's double the amount, and then it's really hard. Well, what does that mean? All right, valence electrons as a review. We've been talking about this a little bit. There's a little dash. You can write this in the upper left corner. Those are the outermost electrons. Just please write that to the right of valence electrons. Outermost electrons. It's in the upper left of your sheet. This is what we're going to be looking at. So like on ours right now, we had one electron on the outer ring of sodium and the outer ring of lithium. That's one valence electron. So here are some examples. And that's sodium's electron configuration. We're going to talk about that. And again, you want to write them all down or not, that's fine. But the last one right there, I know there's a lot there. You can even just write this one for now, if you'd like. Do I have each one typed first? I do, don't I? I'm not trying to overkill this. It's just showing you some examples. What I wanted to show, and I'm not going to go past this slide, is the idea of what a valence electron is. And what it is. And I'm using very similar ones, so I know it seems a little redundant, but it helps us with the chart that's on the back. You have the outer electrons, which are the outermost energy level, and then everything else is called a core electron. Okay? And a core electron is anything that's in the inside. Anything that's in the inside at all is a core electron. The valence are the ones that we're going to be really the most concerned with. So for example, the first one has 1 valence electrons, and you can abbreviate that and put VAL and then E with a negative, right? 1 val E minus. So 1 valence electron. This would have 2. That would have 6. And the last one would have 7. It's nice to see a couple of things that are similar and with the differences that are involved, but it's really important that you're recognizing that like the 3p5 is not 5 valence electrons. It's the S and the P. 2 plus 5 is 7. We have 7 valence electrons. It's going to be extremely vital in where we're heading. Okay, so we're going to do one. Do I have a practice problem? Yeah, I have. Yep. We're going to do one thing with that E738 and 1451, and then we'll go back and finish the last ones here. So I'll give you a second more. I know some of you are still writing. It's important to recognize how these are referenced. So are we kind of seeing, for the most part, you kind of know where to fill it in at least? I would underline these and, again, write at least 1 val E minus and kind of get that all filled out. So if you need something, hopefully somebody next to you has it, or else we can get this filled in later. So you have this value, you just right here, right? This is the last thing on that side. What I need you to recognize is that this value, oh shoot, can you write, I forgot to put these in, put a 1, a 2, and a 3 right here, like little. Please write a little number 1, a number 2, and number 3. And if you're like, I'm not sure, it's kind of written on the top there too. Just write E1, E2, E3. So when you're given this, again, it's not about memorizing this. If we give this to you, and we will on the Twiz or Quest, sounds weird to say, you need to recognize, okay, so that's the amount of energy it takes to remove the first electron. This is of the second. This is of the third. Okay? How much energy? Notice it gets harder and harder to do it. Why? Because every time I remove an electron, the next one is closer and closer and closer to the nucleus, because we just learned that when you remove an electron, the atom gets smaller. So the electrons are getting sucked in more and more and more, and eventually it's going to literally be tucked in right against the nucleus. It's going to be really hard to remove. So you notice there's a huge jump. Like here I doubled and then boom, huge jump. Huge. So make a really bold line there. There's a big jump in energy that must indicate the core electrons. Like I removed the outer electrons and now I went into the inside. Like I am way too close to the nucleus. It's so much harder to remove it. Sorry, I didn't know where I'm at. Because of that, and shoot, I should have written this down. I got to add this. Shoot, I don't know how to write this now. This must mean that I have 2 valence electrons, because it's easier to remove the outer electrons. It's almost impossible to remove the inner electrons. So what that does, we're going to give you a bunch of lists. Like I could say, hey, between all these, is it sodium, magnesium, aluminum, silicon? Which one is it? Well, wait. This has 2 valence electrons. We're going to keep looking at this. Wait a minute, that has S1, S2. Like it only has 2 in the outer energy level. This one must be magnesium, because it's easy to remove the outer electrons. Okay? And when you remove them, we're going to learn in the next chapters that it always becomes a noble gas. We'll get into that later. But if you're going to remove all the outer ones, you'll look like a noble gas. But that is how you read that chart. Just where's the big jump? The jump tells me how many valence electrons I have, okay? So that is something that we'll continue to look at. All right, finishing up, how many more what do we have on the other side of what we're not writing? Okay, I can't trust your sheet, you don't have anything written down. You got 2 left. Electron affinity. Man, apparently I got to make this harder. All right, affinity, you can kind of think of affinity as affection. Okay, so affection, they are gaining electrons. So it's the energy associated with gaining an electron. Now, you might think, well, wait a minute, the last one, ionization, is removing one, so this is gaining, so it's opposite. It's different. When you're talking about the energy to remove, it's how easy it is. This is basically how much, I hate using this because an atom doesn't want to do anything. An atom's not a person, it doesn't want something for its birthday, but the affinity is how much does it want to gain an electron. So, it's kind of like catching something, or like a frog trying to get a fly. If it's really far away, if you're a football fan, unless you're like Odell Beckham, it's easier to catch a ball close to you than really far away. If there's a fly, the tongue on, I just see a frog with this tongue trying to get the fly. It's going to be easier when it's really close. So the smaller the atom, the closer the electron is to the nucleus. The further it is away, the farther that attraction is. So it's harder for it to be attracted to the center. So it is easier for smaller atoms to add electrons because it's so close to the nucleus. Again, if you want to add little extra terms to help you, I'm trying to give you other things that you could be writing. You're closer to the nucleus, so there's a stronger attraction. The smaller it is, the closer you are to that nucleus. And we also learned something else today. There's a shielding effect. So you're actually exponentially making it bigger and bigger and bigger. So I'm really far away. It's hard to get attracted. Think about magnets. The further you move magnets away, the harder it is for those to be attracted to each other. All right, if I'm gaining an electron, what do you think happens to the size? It gets larger. Now there's more negatives than positives. It actually gets exponentially larger. You know, there's actually, to me, a less complicated way of remembering this. Just, hey, I remove an electron from an electron cloud. I'm removing it. The cloud gets smaller. It's made up of electrons. The cloud gets tinier. Oh, I'm adding an electron to an electron cloud. The cloud should get bigger. It is important to recognize the charge. This should make sense that if I'm adding a negative, the atom now turns to a negative ion. Make sure that you're writing that charge. Like I'd stress it, like really make it nice and big. Okay, or unless if you wrote charge. I know the last one I didn't write it this time. So, just going back quickly then, if I have a positive atom, it's smaller, or ion. If I have a negative ion, it's bigger. Okay? Now I know we have one more, but that kind of wraps up the big ideas because the next one's very similar, but we're going to fill in this last one. Okay, and then we're going to do something with a worksheet and we'll see where we're at, okay? So last one's electronegativity. This is going to be really important when it comes to making shapes. So, it is almost the same thing as an electron affinity. The difference is it's when it's in a bond. So they're very, very similar. So that means that it's the same idea. If something's smaller, it attracts it more often. Okay? It's when it's bonded, and we're going to learn that. I will go back. Okay, I just want to see if that was my last slide. All right, so we're going to hand out a little worksheet. If you look at all the trends, keep this out. Francis.
Oh my gosh, it was a scary.
Sorry. Of the 5, get rid of shielding effect for a second. How many are in common just where the D and the I are, besides the shielding? 3 of the 5, right? So the size of the atom, it's I in the lower left, and then D in the upper right. Then the other 3 are the exact opposite. But that's a big deal to kind of recall. So when we're talking about this, we can figure this out. I'm going to steal one. Thank you. Okay, so let's take a look at this, please. You may want to underline things to help you out. So number 1 through 15, but it's odd. The word wasn't very user-friendly with this. It says, which atom in each pair has a larger atomic radius? I would underline the larger atomic radius. So then you're recognizing that. In fact, you could go through all 5 right now. Underline smaller atomic radius, larger ionization energy, smaller electron affinity, so you know which one you're looking at. Okay, now personally for me, this is what I would suggest. You're doing radius. So there's a little open space right here. You could literally just do an arrow like this. And where are the larger atoms? Lower left or upper right? Lower left. So that's a D, or I, and that's a D. Like, oh, you didn't draw a periodic table. I don't need to. I could just do this to help me while I'm going through this section. So just in that open area, that's what I would do. The 1 through 15, I would do a little arrow and just do the I and the D. So let's talk about how we do this. Li or K. So I have Li and I have K. And now it's just important that you're recognizing if you want larger or if you're wanting smaller. So I want larger. So the goal on all of these is I want to find the atom that is closest to the lower left, right? I shouldn't say right, correct? So which one is it, Li or K? K is closer to the lower left than Li. So all you need to do is just circle it. But that's so hard. I wanted to do a square. Then do a square. It's fine. So this one's going to come up, so I might as well talk about it now. Did I do that in the right order? Yep. Let's talk about this one quickly. Fe or Au? Okay. This is the problem. The way that it's orchestrated, it's like, well, that one's higher up, this one's lower, but it's like they're both kind of the same distances. So now, when there looks like there's a tie, this is the only time this comes into play. Shielding effect will take over. As you move down the table, it affects the atom more than when you move across. So let's just talk about this for a second. As I move down, it gets larger, larger. In theory, it gets smaller, smaller. So like, oh wait, it gets smaller one more time than larger, so Au's the smaller one. Every time you move down the table is a much larger effect than moving across once and getting it sucked in a little bit, because I'm adding an energy level, and then I'm adding all those inner electrons, and shielding effect is going on. So here's the general rule. If there looks like there's a tie, the lower one is always bigger. If there even appears to be, my gosh, it kind of seems the same, then the bottom one is always larger. Now, you might be looking for the smaller one. Well, then you circle the smaller one. But because of the fact that these are very, very similar, and like, well, it gets bigger, bigger, and then in theory the trend says it gets smaller, smaller, smaller. It's more or less, it seems even. It's not. Au will be a much larger atom due to the fact that I'm gaining energy levels. Okay, that has a much bigger effect than getting slowly sucked into the nucleus from the nuclear charge. All right, let's take a look at number 17. So next section, atomic radius still, but this is different. Has charges. So this time I want smaller. Honestly, it has nothing to do where they are right now. It has everything to do with the charge. And if you want to look at your note sheet, that's fine. What are the smallest ions? The positives or the negatives? The positive ones. Done. Well, what? When I lose an electron, my electron cloud gets smaller. It gets smaller. Yeah, but what about it on the periodic table? It's going to exponentially get bigger or smaller. And anyway, we're gaining 2 electrons on the O. It balloons out. But I want to talk about this one. They have the same charge. So now that does matter where it's located. So I have CS and I have K. I want smaller. So circle the appropriate one. Well, wait, why are you looking at the periodic table now? It has the same charge, so the charge can't help me. And I want to just do one more so we feel like we've done a little bit of everything. So you can figure that out. Last one. Larger ionization energy. So again, to the right of 29, what I would do is I would draw a little diagonal arrow. What is the answer for this? Okay. This is total. I just randomly picked 3, and it seems like every answer is K. So now you know the secret of the sheet. Just circle K. No, it'd be K because it's smaller. It's higher up. Okay, it's higher up because it has the same charge. Hey, no K. I don't know how to do this one. Na or O? I would write to the right side, an angled arrow again. So now it's, what is it? Ionization energy. What's the rule on ionization energy? They're all the opposite trends of the radius. If you could, studying for a test, if you could memorize that, because it's all about the size of the atom, it increases here, decreases here, everything else is opposite. So this is decreasing, and this is increasing for number 29. Like, okay, yeah, I remember the radius. It gets smaller to the left, gets, bigger on the left, it gets smaller upper right. Okay, everything else is opposite. So I want larger. Which one is it? All it is about vicinity. It's about location. It's going to be oxygen. Oxygen is much closer to the upper right than Na, right? It's not even close in vicinity. So O is closer to the upper right, and I want the larger one. So I circle that. Okay? So when did I make this due? Friday? We're all expecting this to be handed in probably early. Like this, once you get going, it's like circle, 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 circle. But it's due by Friday. So make sure your name is on it. You have an element poster that you should be working on. It is an extremely important grade to start off your quarter, okay? So we have about a minute left. Thank you for your attention.